Hey there, and welcome back. Today, we've got a seriously fantastic math explainer lined up for you. We're going to be tackling a real-world pricing dilemma. You know, the exact kind of financial decision adults have to make pretty much all the time. But we're going to solve it using some incredibly powerful math. I'm so excited to guide you through this, so grab your notebooks, get comfortable, and let's decode some numbers.
Now, right out of the gate, I want to clearly label this explainer for what it is. This is an optional accelerated challenge. If you're already feeling good about grade 7 core math, things like proportional reasoning and one-step equations, this is your chance to step beyond that. We're literally taking a sneak peek right into Algebra 1 territory here. So it's meant to be an enrichment exercise. If it feels a little advanced, well, that's completely by design. You're getting a head start.
Here's a quick look at our roadmap for today. First, we'll review our grade 7 math toolkit. Then, we'll dive into the pricing plan mini project, figure out how to find the intersection, ask ourselves, does this make sense? And finally, wrap up with a project reflection.
Okay, let's jump straight into Section 1, the Grade 7 Math Toolkit, or basically what you already know.
Before we look at any of the new, fancy algebraic concepts, I really want to reassure you that you actually already have the foundational tools required to solve today's challenge. This is the payoff for all the hard work you've put into your earlier math units. From your work with linear functions, you know about the constant rate of change, right? How much an output changes for every single input. You know the y-intercept is our starting value. You know exactly how to build a linear equation in the form of y equals mx plus b. And from your early foundations in algebra, you know how to solve one-step equations using inverse operations. Today, we're simply going to combine those existing tools in a brand new way.
Moving right along to Section 2, the Pricing Plan Mini Project. It's time for a real-world dilemma.
We're going to look at a situation that requires us to figure out which of two completely different pricing plans is actually the better deal. Imagine you want to join a local fitness center, and they hand you this flyer. Plan A has a $10 starting fee, plus $2 per class. But then there's Plan B, which has a much lower $4 starting fee, but it costs $4 per class. So, which one should you choose? Well, obviously it depends on how many classes you take. I want you to look at this and think about how your prior knowledge applies right here. Those starting fees? Yep, those are your y-intercepts. And the cost per class? That is your constant rate of change.
Which brings us nicely to Section 3, finding the intersection. This is where we start visualizing the math.
So to figure out which plan is actually better, we need to find the exact moment when both of these cost the exact same amount. This table brilliantly illustrates what happens as we start, actually taking classes. Let's walk through the inputs. If you take just one class, Plan A costs $12, but Plan B is only $8. So far, Plan B is winning. At two classes, Plan A costs $14 and Plan B costs $12. The gap is definitely closing. But look at what happens at exactly 3 classes. Plan A is $10 plus 2 times 3, which is $16. Plan B is $4 plus 4 times 3, which is also $16. Bam! At exactly 3 classes, both plans converge at $16.
Now, what we just did right there, that was solving a system of equations. This is our big, exciting enrichment vocabulary term for the day. A system of equations is simply when we take 2 equations and consider them at the exact same time, so we can compare 2 totally different relationships at once. Pretty cool, right?
And that exact moment where those 2 plans matched, we call that the intersection point. By definition, it's the ordered pair that makes both equations true. In our table, that matching cost at 3 classes is represented mathematically as the ordered pair 3, 16. And if you're to say, graph these 2 pricing plans on a coordinate plane, 3, 16 is the exact spot where those 2 straight lines would literally cross one another.
I really want to cement this concept, so let's look at a direct quote from our source material here. The intersection tells the number of classes when both plans cost the same. The absolutely crucial point here is that this isn't just some abstract floating math concept. If you know you're going to take more than 3 classes, you can easily look at your data and see that Plan A suddenly becomes the cheaper option. Math literally just saved you money.
All right, Section 4, does this make sense? It is time for a reasonableness check.
As good mathematicians, we always do a reasonableness check. We need a metacognitive step to prove that finding an intersection is mathematically sound without just relying on drawing a huge table. I mean, imagine if our intersection point happened at 150 classes. Drawing a table with 150 rows would be an absolute nightmare. So let's prove it algebraically, using the substitution method. This is an advanced Algebra 1 technique to find an intersection quickly and efficiently. We're going to look at a classic, purely algebraic example, straight from our guide to see exactly how the mechanics of this work in the background. Okay, let's solve a totally new system for the equations y equals x plus 2 and y equals 3x minus 4. Since both of these expressions equal y, it stands to reason they must equal each other at the intersection point. Step 1. Set the expressions equal. X plus 2 equals 3x minus 4. Step 2. We use inverse operations. We add 4 to both sides, which gives us x plus 6 equals 3x. Step 3. We subtract x from both sides, leaving 6 equals 2x. Step 4. Just divide both sides by 2, and we find that x equals 3. Notice how we literally just used our grade 7 equation solving skills to unlock an Algebra 1 problem. How great is that?
But hold up, wait a second, we aren't done. A super common pitfall is stopping once you find x. Remember, our intersection is a coordinate on a graph. It's an ordered pair. We have to substitute x equals 3 back into either of our original equations. So let's just use the first one because it's easy. Y equals 3 plus 2, which equals 5. There it is. Our final, verified solution for this system is the ordered pair 3, 5.
Finally, Section 5, Project Reflection. Let's take a quick look back at what we learned today.
We've covered some truly fantastic ground today, and it is always important to look back and solidify those mental connections. But before you run off to tackle systems of equations all on your own, I want you to lock in these common mistakes to avoid pulled directly from the curriculum guide. First, as we literally just talked about, never give only x or only y. You absolutely need the full ordered pair. Second, forgetting that the solution must satisfy both equations. A pro tip, you can always plug your x and y back into both original equations to check your work. If it doesn't make both statements true, you definitely made a mistake somewhere. And third, simply misreading the graph intersection. When you do graph these out by hand, use a ruler, be precise, and for the love of math, double-check your axes.
To wrap things up, I want to leave you with a bit of a provocative question to chew on. How might you use a system of equations to make a financial decision in your own life? Whether you're comparing cell phone plans, figuring out car rentals, or even deciding between 2 summer jobs, you now have the algebraic power to find exactly where the scales tip. Think about it and see if you can apply your newly expanded math toolkit to the real world this week. Thanks so much for joining me for this explainer, and as always, keep on learning.